Okay, so we are going to move on to another big section. We're going to talk about carbohydrates. Carbohydrates. So first of all is today we also do an introduction for that. So when you see carbohydrates, what this means? This is a carbon, and there is a water there, CHO. H2O. Okay, so M and N. That M could be not equal N. So that's its carbohydrates. So which means it is a sugar. Now we call it saccharides. And where this comes from? This comes from a Greek word called Saccharora, and which means it is a sugar. Okay, so what type of the sugar we're going to talk about? And we know these in the chemistry class. We want to talk about is monosaccharides. So what are the examples? We'll go very detailed today, okay? Glucose and mannose and galactose and lots of others. We'll talk about that. Okay. Now we're going to talk about oligosaccharides, and we also call it disaccharides, and sometimes I call it disugar. So we know the example will be lactose, and the lactose is actually we call it alpha glucose with maybe alpha galactose, and then we have maltose, which is we call it combined by two glucose, which is alpha glucose with beta glucose, and the last one we call it sucrose. Sucrose will be glucose and with fructose. And this is, we know that it's our table sugar, which is made by sucrose. So this is oligosaccharides. Then we're going to talk about these polysaccharides. When we talk about polysaccharides, we mention several things. It's about like starch, like chitin, and the cellulose, and the agar even. Bacteria agar, that's a polysaccharide. Okay, so that's the overall. Now this is overall picture. Here, it doesn't have to be alpha. I just write some there. It could be beta. I mean, I'm just write these, you know. But these are oligosaccharides, which is monosaccharides and combined together. Okay, now something I want to mention is most of these are digestible. Let's say glucose, lactose, these are digestible. Some of these, like cellulose, is not digestible. Even chitin, those are structure, which means they support the structure of the microorganism or biological body. Okay, so the agar, even not digestible. Okay, you make a pudding that is digestible. Make for bacteria, the bacteria is digestible, but people not gonna eat it. So these are the things is like opening remarks we mentioned about here. Then we remove this. We want to talk about the detail is monosaccharides. This is what we're gonna do. Talk about very much detail today. So first of all, so we had a monosaccharides. Okay, monosaccharides, which means they cannot be further hydrolyzed. They are single sugar. Now what are they? We'll give you an example, then we go very detailed. It's 3 carbon to 8 carbon units, basically. The simplest monosaccharides is CHO, this is the carbon, and then we have OH, H, and CH2OH. And we have another one. Another one is CH2OH, CO and CH2OH. What are these two? We mentioned about before. You should have learned about before. This is called glyceroldehyde. And this one is dihydroxyacetone. Those two are the simplest sugar, 3 carbon simplest sugar. Now, what's the difference are they? Now, first of all, these two, the chemical components are the same, and the structure is different. So this is type of is also is the isomer. We call it constitutional constitutional isomer. What's the major difference? You see the carbonyl group or carboxy group, CO. This guy is on the end. And this guy is right in the middle, not in the end. So, this is what we call it aldose. And this guy, we call it ketose. Okay? And when we here, you see this hydroxy bond is on the right side. We also call it a D-aldose. And if this guy moves to the left, we call it L-aldose. Now, in our nature, in our natural environments, most of it is D configuration. So this is just a very basic introduction. Okay, now we wanted to go a little bit more detail. We mentioned about monosaccharides is from 3 carbon to 8 carbon. So what are they? We can draw a figure for you. It's very simple to talk about. So I'm going to draw all the way on the top. Okay, we will use glyceroldehyde to start to do. Why? Because in the food chemistry area, we pay much attention is for aldose. For ketose, we don't talk too much except fructose. And the fructose is ketose. And most of the others, we talk about the glucose, mannose, hexalose, all the others is aldose. Okay? So let's start to talk about it. I draw this a little bit simple. I draw a circle on the top. Then I draw this. And I write here, and I draw a rectangle. So what that means? This circle, which is CHO, is an aldehyde unit. This line here is hydroxy base. And the bottom one is CH2OH. Because otherwise I'm going to draw the whole day. It's very interesting. You could learn this very quick. Okay? So this is the first one. Glyceroldehyde or glycerose. So what we call it? We call it triose. And we use OSE as a terminology. So this is a 3 carbon aldose. Okay, the 3 carbon aldose we're going to go ahead to do. We're going to go ahead to develop. So we go ahead to develop, become a 4 carbon. So what's going to be the 4 carbon we call it? Tetrose. Okay, OSE. So what are going to be the tetrose looks like? It's very simple. Okay, you draw. This has to go a little bit short. Otherwise it's gonna be too messy later. It's gonna draw a little bit short. Okay, like this. This is gonna be like here. Okay, how we do it? The first thing first is always on the right side. And this guy is on the left side. Now what is this one? Erythritose. What is this guy? Sucrose. We don't talk these two too much because in the food chemistry area or biological we don't talk these too much. This is the early stage. Okay, now, so we're gonna go here. We're gonna talk about is called 5-carbon. 5-carbon aldose, what is that? Pentose. Okay, so we're gonna move it. Okay, and I probably have to move some here. What gonna be looks like? You go down, go down. This go down, go down. So this is what we're gonna draw. This will be draw this a little bit better. Sorry. Sorry, we should be drawing this. Let's draw this. What are we gonna do? One there, right side, one left side. This is a bigger one. What's that? Ribose. What is this guy? Arabinose. Okay? Now, this guy here, we have to move a little bit. Okay, we work here a little bit. So we're going to draw. This guy goes here. And then here. This guy goes here. Then what is that one? The other one is called Exolose. What is that guy? Lysose. What are these called? Pentose. That's 5-carbon. Okay? Ribose. This is the basic units of RNA. If 3' deoxyribose, that is DNA. You know about that. Where they come from? Pentose phosphate pathway, they gave them a precursor. Okay, then go down. So they're gonna become a big guy. Right here. Okay, so same thing. Go here. 1, 2, 3. Go here. 1, 2, 3. Again. Right side, left side. What is this? Allose. What this guy? Ultrace. Ultrace. Okay, arabinose gonna come out some big one. Right here. Do here. Draw. here, here, here. We have a tail. This is going to be right here. Okay, then we go here. Here. Let's go to the left. What is this guy? Everybody knows this is glucose. What's that? Mannose. We will back to talk about this real quick. Okay, Xylose. We're going to draw right here. Xylose goes here, go down. We do 1. Add one on the right. And then this guy, go here, this one on the left. What is that one? This one, glucose. We don't talk too much. Okay? We don't talk about this guy too much. This guy, idose. The last one. Okay, we're going to draw here a little bit. The last one. So Xylose move here. And you go here. So we have one on the right and one on the left. What is this guy? Galactose. Lactose. What is this guy? Tyrose. Now, what is this called? Hexose. 6 carbon. In the food microbiology area or food chemistry area, this is almost 80% we care about. Okay, 5 carbon and 6 carbon. You can go down. So we want to mention several things. First of all, is glucose and mannose. Okay, so we're going to take them up. Glucose and mannose. So what is glucose? You can draw here. CHO goes here, become OH, H, and go here, HO, CH, then go here, become COH, H, and go here, COH, H, here, CH2, OH. This is glucose. Okay, what is mannose? CHO, in the opposite direction. So O H HO H CH OH CH OH CH2 OH. What's the major difference? Right here. How we label them? 1, 2, 3, 4, 5, 6. Okay, this is called carbon 2 epimer. Remember, glucose and mannose, there's only one difference. It's right there. Okay, how about the glucose and the galactose? What's the difference? Is that right? So what we call it? Carbon 4 epimer. Okay, so that is called an epimer. Okay, then, how about ultras and glucose? is a fundamental difference. These type of isomer, steric isomer. Also another isomer. Okay? So these are the things we mention about in the organic chemistry. We just want to give you some of the overview. And then we want to talk about later on a little bit more detail. Okay? So here is the thing we want to talk about is glucose. So we take this out. Talk a little bit more. Okay? And I'm going to draw a little bit more. So I take this out. So we want to focus on glucose. Because lots of things come from glucose. So what is glucose? CH, carbonyl group, carboxy bonds, and it's aldose, aldohexose. So we go here, OH, H, here, H, O, C, H, go here, OH, H, here, 1, 2, 3, 4, CH2, OH. Okay, we mentioned this. 1, 2, 3, 4, 5, and 6. First of all, what's the name of this type of the configuration? Fission projection. Okay, what the Fission projection means? Fission projection could be kind of like this, like perpendicular and horizontally. So we always call this is it's a wedge, and then we go out. Slash. So two kinds of the form, the slash form and the wedge form. Okay, so we go here. And we think about this angle is probably 90 degrees, but I tell you in real life it's not. It is about 109.5 degrees. We talked about this before. This is also called tetrahedral arrangement. Now what is it going to be looks like? Why it's going to be looks like this? Because your eye goes this direction. Around the 45 angle, you watch like that. Now some textbook said that this is like your airline, go back to the airport, and some of like how you flee away. Okay, let's talk about this wedge and slash. So this is the first thing. This is called the Fission projection. Now we want to mention here. The Fission projection could be changed to another configuration, which is called Hayward's configuration. You heard about it, you know about that. So what is that? What it is? This is the one we want to mention, is this carbon 5. There's some story behind this. This carbon 5 is a hydroxy bonds. This is kind of like alcohol. Not really alcohol, it's alcohol. There's people saying this. Then inside of this molecule, we call it intramolecular attacking. They're gonna go ahead to attacking this guy right here. This is the aldehyde base, carbonyl, and also because carboxy base. They're gonna attacking this O. Okay, so what is it gonna be looks like? Then this is intramolecular, which means inside of the molecule, not outside, internal attacking. So what is it gonna be looks like? So you know it's going to be looks like a ring. Okay, but there's some story we can talk about. What it looks like. Originally, we start from the carbon number 1. Okay, this is carbon number 2, number 3, number 4, number 5. What it looks like. It looks like this. Now, how are you going to label these? Start from this OH. The very easiest way to do is this turn 90-degree perpendicular angle. Okay, like this. So this OH is go down. So this OH is going to go down. This OH, H. Of course, it's go up. H. OH. H. It goes down here, become OH, H. Now something going to happen there. Originally, it should be OH and H. And then here will be CH2OH. That's what originally should be. Then, if this happened, what are going to be looks like? This is oxygen right there. Okay, this oxygen will be connected with this carbon, and this guy will connect to go here. So what it looks like? CH2O will C OH and H. This is what originally looks like. However, if this happens, we have a problem. This is called 7 chemical ring. If this 7 chemical ring happened, this structure from the energy standpoint is very unstable, because the energy we always have to control in the minimal status. Therefore, in our nature, in our natural environments, we reject this. Okay, we cannot accept any 7 chemical rings. So we reject this. Now what are we going to do? And luckily, we can do something, because what's the bound of this? This is covalent bonds. The covalent bonds, they can turn an angle. They can do a rotation, which is 90-degree rotation, and then will be present the O to the aldehyde groups there. So then what is going to be looks like? So we can draw another picture right here. What is going to be looks like? We draw it, okay, again, to make sure you understand it, because these things are important. COH, H, OH, OH, H, OH, H goes here, and this goes up. So CH2, OH, and H, and here is COH. Okay, and here actually is OH. And I also, when we draw it, I'm going to draw this H a little bit far away like this. Okay, now what's going to happen? This O is connected with, there is an external dipolar electron. Is that right? Available. That's delta negative. How this carbon here? This carbon is delta positive. So therefore, they could connect it. But how about this guy? This guy, this bond, they're going to be deleted, going to be released. And then right here, what's happened? This guy going to go here. Therefore, it becomes a structure like this. And this is go. Okay? That's what it looks like originally. Now, once the Fission projection become a Hayward's configuration, something you notice that it's going to change. What is that? This becomes a new chiral carbon center. We call it anomeric carbon. It's a new carbon center. So, how many other chemicals surrounded it? So surrounded one is number 1, number 2, number 3, number 4, and the number 4. Sorry, 1, 2, 3, 4. They surrounded that. About here, how many they surrounded? 1, 2, and 3. Okay, then comes out with what? How many chiral carbon? Which is 1, 2, 3, 4. So there's a 4 chiral carbon there. How many chiral carbon here? 1, 2, 3, 4, 5. So 5 chiral carbon. So what this means? From the Fission projection transfer to Hayward's configuration, you all add 1 chiral carbon. That's what's a major difference. Okay. Now we want to go back to talk about here. This guy, if we delete it, we make joints a little bit easy right here. Okay. We come out with this guy is go down, and this guy is go here. What is this called? Alpha anom. Okay? If this guy goes up, is beta anom. Now, in order to well describe this, can you move the camera, Michelle? In order to well describe this, they comes out with another configuration. Chair configuration. Configuration. So what it looks like. Okay, this is gonna become like that. Okay. So how are we gonna do? We have to do the label. Carbon number 2 is carbon number 1, number 3, number 4, and number 5. So what it looks like. This carbon number 1, this H is always on the top. Carbon number 3, this H is down. This H is on the top. And here, this H is actually down. And here is CH2OH. The position of this H, we call it A axial. Now, the position of the OH like this, hydroxy bonds like that, and also like this. How we call it? Equatorial position. Okay, that's a chair configuration. Now, what's the difference between the Hayward's configuration and the chair configuration? Hayward's configuration, you could see is a spatial view. You will see very clearly is a spatial view. Now, for the chair configuration, you can see this type of the angle. So here comes this carbon number 1. Okay, if the carbon number 1 is something like this, go down. This is called alpha anomer. If we do the opposite direction, this go up, hydroxy bonds go up, H go down, this is called beta animal. Now, here comes another important concept. We dissolve our sugar, let's say glucose. It's a crystal. Okay, we dissolve in water. Once it dissolved, what going to become? It's not only going to be the glucose. There is a 4 different type of the configuration there. And 2 will dominate, which is beta animal and alpha animal. And in our real life, in the natural environments, beta animal is about 64%, and alpha animal is about 36%. And this gives you another terminology, we call it mutarotation. That gives you another terminology. Okay? Another thing I want to also mention, these type of the ring. When here you see there's a 6 carbon, and we also call it a pyranose ring. Okay, if it's 5 carbon, furanose ring. Okay, so here's something we want to mention, the chair configuration. Now there's a question for you. Very simple question. This is the one is we write is alpha glucose. Okay, if I want to write alpha galactose, I have a question. If I don't want to do alpha galactose, what is going to be the chair configuration looks like? It's very simple. You don't have to redo it. Why? Because the galactose and glucose, looks very similar. There's only the carbon 4, the configuration is different. We call it a carbon 4 epimer. So what's the difference? The only difference is this guy go up, the OH go up, and the H go down. It's so simple, it becomes galactose. Okay, the same thing, how about the mannose? The carbon number 2 is go up and down. It's a very simple and very tricky organic chemistry question, but when you're using a chair configuration, so you can understand it. So what I'm talking about here is give you a review of the Fission projection, Hayward's configuration, and also the chair configuration, all those 3. Okay, they added up together, so you have a basic knowledge about that. Okay, then we want to mention something else. Well, this is the glucose. Okay. This is the glucose. We know that. I usually going to draw a beta one. Okay, we want to talk about some of the glucose derivatives because it's important. Okay, move the camera a little bit to make sure it's all covered. Thank you. Okay, this is the glucose. This is the glucose. If this guy is gone, become this. What is this called? N-glucose-CME. Is that right? Okay, if this is glucose-CME. If I add up here, N-acetyl glucose-CME. Okay, I'm going to draw another one right here. If I have another one. Okay, OH, this here will be NH2, C, H3. I go here, we're going to have an all subunits here. Okay, this is OH, H, CH2, OH, H. What this all looks like? This all will be CH3, COH, and COO. Then what is that? N-acyl uramic acid. What are these? MUC. Do you remember what is this? Peptidoglycan. If they cross-linked with amino acids. That's what the word comes from. Okay. Do you still remember in your biology class, microbiology class, what is this? Fluid mosaic model of a cell membrane. Think on top, it's very heavy peptidoglycan. And outside, you have these teichoic acids. This is very heavy for gram-positive bacteria. Then this comes with gram stain. Is that right? So, this is something I want to mention here. This is in the food chemistry class. We should mention this is what is N-acetylglucosamine and acetylmuramic acids. This looks like that's a major derivatives of the glucose comes from. Okay, so this is something I want to mention. So we want to move this out. We talk about this detail in general microbiology class, in another class. So we don't mention here. Then we want to talk something else. Okay. So we go back to this glucose right here. Okay, we want to mention this glucose, CH. I always like to draw because when you draw 1, 2, 3, 4, 5, 6. When you draw this, you will be understanding the structure and what's the story behind that. And this is okay. What is fructose? This is glucose. What is fructose? This goes here. Okay, of course the top gonna change. This becomes a fructose. Okay, very simple. It's a keto hexose. Okay, we don't want to talk about this too much. I will talk about it when we talk about the oligosaccharides next section. What I want to mention is we go back to glucose. We go back to glucose. There's something is interesting. And as food microbiology nutrition students, you know about this, but you don't realize it. If I do something on this carbonyl group, carboxylanes, I add this guy. This is a hydrogenation happened for the glucose. What it becomes? Okay, CH2OH, CHOH, C. What is this guy? Michelle, can you tell me what is this guy? You're a dietitian major and dietitian student. What is this one? It's a sugar alcohol, sorbitol. Okay, that's sorbitol. Because very simple. Just write on the top. That's called hydrogenation, which is sugar hydrogenation. Okay, quotation mark. Hydrogenation. We mentioned about it in our fatty acid section a lot. Carbohydrates could happen the same thing. It's the same. You add a bubble, air bubble, the hydrogen ions, and you have like a catalyst which is a nickel. You close the vessel, they do the same thing, become a sugar alcohol. That's a sorbitol. Now, there is the three major sugar alcohol, which is using a lot in the food industry they talk about, is sorbitol, mannitol, and xylitol. So what's the difference? Sorbitol, ITOL, this means a sugar alcohol. Okay? Now, by the way, I forgot to mention, OSE is a aldose. How about ketose? ULOSE is ketose. That's all the same. Just change the UL there. So that's sugar alcohol. What are those used? Sorbitol, and a little bit like syrup, okay, crystal. What's a mannitol looks like? When you cough, you have a cough drop. They use other mannitol there. And they also mention it's called a non-sugar,